Good morning, everyone. Morning and welcome to everyone to our research school. Shall we get started? So welcome, everyone, and thank you for coming. Thank you for coming, whether you travel from abroad or from within the UK, or if you're just local and dropping by. Before we start our first set of lectures, I'd like to say a few words of introduction. So machine learning and more generally artificial intelligence is a set of tools that many of us have started using in our research in the last 5 to 10 years, following several developments, right, which have convinced us that this is something worth learning, like the AlexNet in visual recognition, AlphaGo, and more recently the development of transformer techniques in natural model and natural language processing, such as ChatGPT. As you will have learned by the end of this school, machine learning is not just one recipe, and indeed it comes in very many different flavors. But what is common to all of these techniques is that the focus on the development of algorithms that allow the computer to make predictions and decisions without being explicitly programmed to do certain things. So it is this element of getting out of the computer more than has been put in that makes machine learning approaches revolutionary, opening up new horizons in terms of opportunities, but also challenges in terms of our traditional scientific methods, which rely on explicit models and equations. So we will have the chance to reflect on these opportunities and challenges during the panel session that we scheduled for Wednesday afternoon. So please join for that. Looking at the program, what lies of us is a very busy week. And while most of us have heard of machine learning in one form or another, not all of us had yet acquired a working knowledge of the techniques involved. So this summer school brings together experts from around the world, 8 lecturers and 7 tutors, to tell us how they incorporate machine learning in their research and how it helped them to solve certain technical difficulties that they encountered in their research. So I think this is the best way of being introduced to this topic, to have our colleagues telling us how they are using machine learning and why this is something worth learning. The school is sponsored by our friends at the London Mathematical Society, and without their help, we wouldn't have been able to offer the support that we offered. So free accommodation for most participants, and school dinner, free lunches, coffee breaks, and travel support, and so on. So I have a few slides that I'd like to go through, which introduce the London Mathematical Society. So this is a major UK society for mathematics with national and international membership. They have over 3,000 members. It was founded in 1865 and was granted a royal charter in 1965. The main activities of the societies include publishing journals and books, providing grants to support mathematics, and organizing scientific meetings and lectures. The society is also involved in policy and strategic work to support mathematics and the mathematics research community. So if you become a member of the society, you'll have the chance to sign this book. And in the members book, there are names such as Augustus de Morgan, if you remember it from logic, and Henri Poincaré, G.H. Hardy, and Mary Cartwright, and Maxwell, and many others. So you can apply for membership by visiting the LMS website. There's a link here. And there are many benefits which come with a membership. So there are opportunities to apply for research grants and to attend society events and influence national policy. The LMS has published mathematical texts since its foundation in 1865. These are international publications critical to the society's delivery of its activities. And the society has been fortunate over its history to receive several significant donations and legacies, among those from Ruehle, Larmor, Hardy, and Fröhlich. And of course, these are extremely important for the running of the society. So before I hand over to Fabian, our first lecturer, let me say a few practicalities. On Thursday morning, there will be a fire drill, but other than that, we don't expect any kind of fire alarms. If they set off, these are the exits, the fire exits, and the assembly point is in front of the university parks. There are toilets, which you can find behind the lecture theater. There will be a coffee break at 10:30, and then lunch will be served in the foyer, so the area where you have signed in at 12:30, I think, so after the second lecture. And this pattern will repeat every day. In the afternoon, we'll have tutorials. There is a coffee break between the two tutorials also. Yes, and if you need any help, I have some helpers here. So Lucas will help us, and Pete and Thomas. You'll meet Thomas as a tutor as well. And many thanks to Young, who's organizing the conference with me, and to Michelle, who helped you sign in. I'll hand over to Fabian. So Fabian is going to introduce some basic techniques in machine learning. Fabian Ruehle is a professor of theoretical physics at Northeastern University, and he's one of the pioneers of using machine learning in theoretical physics, in particular in string theory. Okay, thank you, Fabian, and it's over to you.
All right, can you hear me? Well, thank you very much to the organizers for inviting me to give this series of lectures in the school. I'm really looking forward to the week. I think we have a fantastic set of lectures lined up, and I think I will learn a lot. So thank you very much. I have the honor of giving the first lecture on this topic, Introduction to Machine Learning. And when I was preparing these lectures, I was really torn on what to present, because we have 90 minutes and this topic is huge and it's growing. And there are so many there's been so much important progress in this field within the last decade or so. Andre mentioned a few things, AlexNet and so on. So I was really not sure what to do. And I think more recently, there have been essentially two things that really put AI in the focus of German public. And one of them is diffusion models. So you've probably seen images generated by DALL-E, for example. And the other thing is ChatGPT. So that is the transformer architecture that Andre was mentioning. And I decided I will go with the transformer, because I think very little inventions have changed the world in a way that the transformer has. So it's a very exciting time. We will see where it leads in the end, but I think nowadays, if you enter the topic and if you give a school in machine learning, you should actually know what the T in ChatGPT does. I won't have time to explain ChatGPT itself. Of course, there are many additional things to be said, but I will explain sort of the transformer, the underlying architecture, the idea that started it all. But before we go there, I will sort of start more basic. I will introduce neural networks in general, and then I will explain how these things actually learn. And then in the second half of the lecture or so, I will then focus on the transformer. Please feel free to interrupt me at any point if you have any questions. I hope this will be very interactive. I have prepared not so many slides, so I think I will be able to get through them and still have a lot of time for questions and interactions. Good, so let's start with neural networks. So as you can see in this title slide, usually neural networks are represented by a graph like this, and they are really modeled after the human brain. That's where the name comes from. So the idea was, in the human brain, you have cells that transmit information with electrical signals between them. And to mimic this, you have sorry about that, I don't know what happened. So to mimic this in the neural network, you have different nodes and they are connected to one another, and then sort of signals are propagated from one side to the other. So this is historically what people thought they should build when they started to talk about artificial neural networks. Of course, there are many, many ways of introducing this, and for the purpose of this lecture, I want to actually take a different point of view, a little bit more of a mathematical point of view, maybe. So for us, a neural network will just be a family of maps, or just a function that has some parameters in it. You can think of a neural network as mapping some vector in some R and in-dimensional vector space to some R in out-dimensional vector space. And this map has parameters in them, which I collectively call theta here. And how do you build this map? Well, there are tons of ways. Of course, you can write down a map, and in neural networks, sort of to mimic this layer-wise propagation of signals, the way it is done is you take this vector here, you multiply it by a matrix, so that maps it, let's say you have a 3-dimensional vector, you multiply it by a 5 times 3 matrix, so now you have a 5-dimensional vector. And then you can add a 5-dimensional vector to it. And these are called the weights. These matrices are called the weights, and these B's here are called biases. Now you have a transformation that mathematicians call this an affine transformation from R to the 3 to R to the 5, let's say. Or in this picture, it would be from R to the 2 to R to the 3. Now we have a 3-dimensional vector. So now what you could do, of course, you could multiply it by a 2 by 3 matrix, map it back into some 2-dimensional space, and that's it. But if you just did this, your neural network would not be very powerful. In fact, you can show that, of course, if you multiply by matrices and add a vector, and you multiply by a matrix and add a vector, you have a concatenation of affine maps, and that is just by itself an affine map. So you could just learn an affine or linear function in this way. So to make them more powerful, you actually need to do something in between. And the something is you add an element-wise nonlinear function here. Which function? Well, who knows? Just add any nonlinear function. In this example here, you add a hyperbolic tangent. That might seem like a little bit of a weird choice for a function, but I will explain later why hyperbolic tangents are actually feature quite prominently in machine learning or in neural networks. Functions like the hyperbolic tangent. So overall, this map, this parameterized map would be essentially you multiply this thing here by W matrix, and you add a bias B to get this. Then you take the tanh, and then you multiply again by some 2 by 3 matrix, and you add a 2-dimensional vector, and you get the final output. So this is what a neural network does. It is a map from, in this case, R2 to R2, going via some 3-dimensional vector space with some nonlinear tanh in between. And these W's and B's, all these entries of all these matrices, they are just the parameters that I collectively call theta here. So this might look a little bit strange to you to write down a function like this. I mean, obviously it is a function. It's completely explicit. You can see it here. You can do whatever you like with it. You can differentiate it. You can integrate it. You can do whatever you can do with the function. So neural networks are, sometimes people say neural networks are black box. Well, that's true, but they are not black box in the sense that you don't know what they are. This is the function. It's on the screen. You can see it and you can do whatever you like with it. Just people, you can't understand them really. This is, ironically, they are modeled after the human brain, but this is not what the human brain, or how the human brain thinks about functions. But of course, parameterizing functions is nothing that you see for the first time here. So probably you've all seen Taylor expansions. So a Taylor expansion would be typically of the form z minus b to some power times some w, where this w would be the nth derivative of the function. So this looks kind of similar to this approach here. And for example, in Fourier expansion, you just expand this in cosines with different amplitudes and different frequencies. But this way of thinking about function expansions is more like what physicists or maybe mathematicians or people who need to understand what a function does actually like. Because if you have a Taylor expansion, you can think of all of the higher terms in the series as sort of higher curvature corrections, higher derivative corrections. And in the Fourier decomposition, you can think of it as sort of higher and higher frequency modes. Neural networks don't have this interpretation. It's just these functions and whatever these parameters do will change the function. Of course, if I put 1,000 here, this will be different from putting a -5 here. But it's much harder to actually understand how these parameters change the function. So your question might be, why would you ever want to do this? And the answer is that neural networks are universal function approximators. So this is a theorem that's actually very old. It's from '89, has been generalized later, but this is more than 20 years old now. What this means is, under some mild assumptions, that your neural network can learn any function if you make it big enough. So in particular, it can learn the function you're interested in. Yes, please. Yes, that's a very good question. So the question is, what goes into the theorem? So as I said, there are some mild assumptions about this theorem. So the image should be compact and so on. And so Cybenko proved this for a very specific set of functions. So Cybenko's original proof was about a neural network that has one layer in here. This layer is getting infinitely wide, and this activation function is actually something that looks like a tangent. It's what's called a sigmoid function, which essentially goes between 0 and 1. It's e to the 1 over plus, it's 1 over 1 plus e to the x, or wx plus b. And so he proved this originally for this, but then this was generalized, and in fact, any non-polynomial function will do. This is what was shown later. So when I said we choose the tangent here, or Cybenko choose the sigmoid, it's easy to prove it's easier to prove in this case, but for the purpose of approximating a function, of having the universal function approximation property, it doesn't matter as long as it's a non-polynomial function. This doesn't mean that sort of all of the nonlinear functions work equally well. I mean, the neural network might still be able to learn one function easier if you use a tangent basis versus a reloop basis or so for the functions. But in principle, I mean, this is a theoretical result. As a theoretical result, it doesn't matter. So what do you have in mind, like making this already quadratic or something? So you can prove that if you, the reason why polynomial functions don't work is if you have a polynomial activation function, all you will ever get out is a polynomial. So you would never be able to get out something else. Yeah, I understand. But if you have like an x, I mean, sort of the linear map is already the simplest one that works. If you make it more complicated, I mean, in particular, every quadratic function is, I mean, you can make it linear again, and then it works for a quadratic function, it would still work.
Does it have to be organized in layers?
Very good, very good. Yeah. So the question is, in here we have sort of the sequential map. We map from R2 to R3, then we apply nonlinearity. We map from R3 to R2, we apply nonlinearity. This is not really how the brain works. The brain has all these interconnections, and it goes back and forth. And I mean, nodes are connected in many different ways. So if you do this, people have set up like bidirectional neural networks of stuff where everything is connected to everything. Boltzmann machines are an example of that. It's much, much more difficult to train these things. So this is an assumption that is made to make them easier to train. One thing that's done very, very frequently nowadays is actually to skip certain layers. So you would not just connect this node to this node, but also this node to that node. So that's yes, we will get to what the bias is doing later. But yeah, it's similar. Good. So one way of seeing why this is true for the sigmoid function. And again, here I'm very hesitant to include this because what I will give you is a proof that you can approximate any function, but this is not what the neural network does. This is a mathematical proof that it's possible, but it's not what the neural network does. So here's the proof. So you can take activation functions like the sigmoid in this case, or the tang in my case. So if you plot tang of x, it's just this graph. Now you can ask yourself, okay, so now I have these, let's see what happens if I plot tang of 20x. This almost becomes a step function. And then if I add a bias either here, I can move this curve, and if I add a bias inside the tang, I can move it left or right. And in this way, so now if let's say I take this tang of 20x plus 1 minus tang of 20x plus 10 plus 1, I get this step function. Once I have the step function, I'm in business. I can just approximate this essentially with these steps. And if I have enough nodes, I can make these steps as small as I like. So I can get sort of arbitrary close approximations to this function. This is roughly what Sabenko proved in '89. But again, this is not what the neural network does. This is extremely wasteful. You're wasting tons of nodes to just build these steps. There are much more efficient ways for a neural network to represent a function. Okay, so in practice, nobody sort of builds this neural network that Sabenko had with one layer that's infinitely wide. I mean, obviously you can't build it infinitely wide, but you could make it 10 billion nodes or whatever. This is not what people do. This is not how neural networks are built. So instead, what you do is you take a neural network, you make it very finite, I don't know, like 100 nodes, 1,000 nodes, but then you make it deeper. So instead of just doing this once, this step here, just doing this once, you do it many, many times. So you have many of these intermediate layers. They are called hidden layers because you don't look at the output. So you do this, you have many, many maps from Rn to Rn to Rn, or from Rn1 to Rn2 to Rn3. And then in the end, you map this to the output you're actually interested in. So you're building this function that you're interested in. You're building it up by, again, matrix multiplication and adding vectors and applying nonlinearity. So you will get something like tang of W of tang of W of tang of W plus B plus B plus B plus B. And so on. So this is what the function is. It's still completely explicit. It's still not interpretable. Good. So now we know you can learn a function with neural networks. How does this help you for the task you're interested in? Well, I said it can learn any function, so probably can learn the one you're interested in. Probably can also learn all functions you're not interested in. That's another problem. But so if you have tasks like, for example, learning regression of a function, of course, this is obviously some sort of fitting a curve, but also for classification, what you do is you learn a decision boundary. You learn like this graph. If the task was to distinguish the red dots from the blue dots, you would still learn some function that sort of is the boundary between these points in whatever the input space was here, whatever the input layer was representing these dots as. And of course, in general, you need some highly nonlinear function, but you can learn this function that delineates sort of the red from the blue. And then you're able to predict cats from dogs, let's say. Good. So this is all that I wanted to say about the standard neural network at this point. So the one thing that I introduced is what's called sometimes a multi-layer perceptron or feed-forward neural network with a certain depth, meaning a certain number of hidden layers and a certain width. And of course, now you can add tons of bells and whistles, and people have added tons of bells and whistles to this. This is not even the AlexNet that was maybe the first breakthrough, but it is essentially what underlies all neural networks. So all neural networks have the same idea. You multiply by a matrix, you add a bias, and then you choose these parameters in these matrices until you get the function you want. So this idea is common for everything. And then there are more sophisticated things, like I said, for example, to Steve's question, there's chip connections and so on. Are there questions on on this first part, on the feed-forward neural network. Okay, good. So the second part is, once, of course, we have set up this function, the question is, how does it learn anything? How do we train it? And in principle, the training process will be to just change these parameters. These parameters will in some way change this line here, because that's the function that it learned, or this line, and it will change it until it essentially goes through all the points we want it to go through. And that's what's called a backpropagation. So this part will be a little bit more technical. There will be a few equations on there, so I apologize in advance, and I will give you sort of just the general idea in advance. So in machine learning, there are different types of machine learning. There's supervised machine learning, there's unsupervised machine learning, reinforcement learning, self-supervised learning, and so on. There are many different things. When we talk about a function learning something, you typically, what you mean is you find a function that is input dependent, of course, and it produces the output that you want it to produce. So you have a notion of what you want to get out of this function. Maybe a line that tells cats from dogs, or maybe a function that sort of interpolates or regresses a given set of points. They have a notion of what you actually want to achieve. And this notion is encoded in what's called a loss function L. And what this does is it gives you the distance between what the neural network predicted and the output that you actually want to have. So we have some input X, and we also have some output pair Y of X. So now what I can do is I can feed X to my neural network and just see, I mean, it's a function. I give it a value, it returns a value. That's what a function does. Of course, the value that it returns will depend on these parameters. But if I have a notion of how far away I am, what this output is from what I actually wanted to have, then I can define a loss that actually tells me how bad I am. So the neural network was supposed to predict 5, but the answer is 2. So I could, for example, assign this a distance 3 between the output of the neural network and the output that I want to have for this point. And then the name of the game just becomes to change these parameters data until you get the output that you want. So you're changing the function, the way the function is parameterized, you're changing it until it produces the function that you like to learn. And typically you choose loss functions such that they are larger than 0, or larger than or equal to 0, and they're equal to 0 precisely if the neural network at the point is, sorry, that should be an X. If the neural network at the point X is equal to the output that you wanted to produce. So that's the idea. It's also common to all neural networks, but this, of course, gets exceedingly difficult. If you look at ChatGPT, for example, you have billion-dimensional parameter space that you need to find the optimum in. So you have a billion parameters, and you don't really know what changing each one of them does. So you have to change a billion of them all at once in a way that this highly nonlinear function somehow produces the output that you like. And this type of optimization task is extremely, extremely difficult. So essentially what people do is they do the cheapest or the simplest thing that you can do. It's a linear optimizer's gradient descent. There are, of course, much better ways of finding a minimum in a function. So you might have heard about Newton's method or whatever. But that would be second order, but that's too expensive to compute in a sense in a billion-dimensional parameter space. So people have found that just using this linear method of finding the minimum, this is very fast, and you just do this over and over again, works extremely well. You find minima that produce something like ChatGPT for you. So what is the idea of gradient descent? Well, gradient descent is essentially the idea of going down in the loss until you reach a minimum in the loss. If you reach 0 in the loss, as I said, typically you set up your loss such that if it is 0, you have learned, at least at the points that you input, you have learned precisely the function that you wanted to learn. So here I've plotted a random loss landscape. So this would be not the function that the neural network learns. This is the loss. So what I did is I gave my neural network, I took a neural network, I had some loss function, I had input-output pairs, and for different inputs in this two-dimensional R to the 2, I computed what the neural network gave me, I computed what I actually wanted to have, I subtracted them, I took the absolute value squared, and you get a picture like this. And now what you want to do is you want to find the minima in this loss landscape, because that's then where the neural network produces the function that you want to learn. So if you first fire up your computer and sort of set up the neural network, these parameters theta, or these W's and B's, they have to be something. And there's a lot to be said about initialization of neural networks as well, and I have no time whatsoever to go into this, but you assign some random value to all parameters in your neural network. So you have a billion random parameters, you just draw them from some distribution, you put them into your matrix, you multiply, and that's what your neural network is. So randomly, you will be at some point in this loss function, because your neural network was initialized randomly, and if you sort of repeated this experiment, you would be sitting somewhere else in this loss function, because you would be learning a different function, or you would be starting with a different function every single time. So now what gradient descent does is, well, it finds the gradient of the loss function, and you sort of continue for a while along the steepest gradient in the loss function. So you update your parameters such that you're going towards the minimum of the loss function. This is akin to essentially, if you're on top of a hill and you want to go down into the valley, you just stand somewhere, you look around where the steepest point of descent is, you take a step there, and you wait there. And then you check again where the steepest descent is, you take a step, and you re-evaluate. And you do this over and over until you find some minimum. Of course, just this analogy with sort of descending a mountain tells you I might never get to the valley. I might be sort of trapped in some local minima. I might go there, and now from everywhere now it's going up, but I haven't reached the valley yet. So gradient descent is not guaranteed to even give you the global minimum. It's not guaranteed that you will ever get to a point where the loss function actually is exactly 0, or where all your input, where the function that you are parameterizing with the parameters that you found actually produces the output that you want at every point. But typically you find minima that are good enough, in a sense. You're very close to what you want. And moreover, even for points that you haven't seen, it's doing the right thing. It's producing information that it's producing a function that gives you answers for points it hasn't seen before that are very sensible. Good. So the question is, of course, you can take 1 step, you can take 2 steps, you can take a zillion steps. So what's essentially a good way to go? So if you have a good learning rate, essentially what you would do is you would take steps and you would just sort of walk into this minima and be done with it. If your learning rate is too big, or you get this sort of behavior, you just jump all over the place. So this was a learning rate of 2, I think, in this example. And you just sort of, you don't converge because you're just stepping over the valley up next again before you check again, and then you never sort of end up where you wanted to end up. In this case, yeah, you would just find chaotic, oscillatory or unconvergent behavior of your neural network. If it's too small, what can happen is it just inches towards the right thing, but it doesn't converge in any sensible amount of time. We don't know how much it costs actually to train ChatGPT, but tens of millions are estimates. So you can train this thing exactly once. And if you do this and you end up essentially here instead of there, you just lost 10 million. So choosing the right learning rate is quite important and actually a quite difficult thing. There are many different optimizers that you can add to this idea that sort of dynamically updates the learning rate, tries to guess good learning rates, includes other information of the function and so on. But again, this is not something I can cover in this lecture because then I wouldn't be able to talk about the transformer in the end. Good. So here's an overview of different loss functions you could envision taking. The loss function itself depends on the task you have. In all cases, you need some metric. You need some notion of distance of how far your prediction is away from what you want to get. And the easiest thing is what I briefly mentioned previously. It's what's called a mean square error. So you take essentially the label that you have, the output that belongs to the input, you compute what the neural network gives you for the input, you subtract them and you square them and you sum them all up. That's why it's the mean, and of course it's a square error here. Another possibility, instead of squaring it, would be to take the mean absolute error. So you just subtract the absolute value. Of course, we always want this to be positive, so we take absolute value square. You could take any LP norm there, but it should be positive and it should be 0 if essentially the answer from the neural network is equal to the label that you want to predict. There's something that's called the mean absolute percentage error. So you do essentially y minus f divided by y. This is only a good idea if y is not equal to 0, of course. So which one you take depends a little bit on the task you have at hand. For classification, people usually use what's called a binary cross entropy, at least if it's a single class classification. So the loss function looks a little bit more complicated. I apologize, this should be f sub theta. So the idea is, in this case, you have, you want to tell cats from dogs. So that's a classification task where the answer is either 0 or 1, cat or dog. And if you look at this function, let's say if the answer is 0, let's say the answer is 1. It doesn't matter. Let's say the answer is 1, and the neural network predicts 0. And this term will be extremely large because you were wrong. The answer was 1, so this term will be 0, so this term will be extremely large. If the answer is 1 and the neural network predicts 0, then this term, so if the answer is 0 and the neural network predicts 1, then this term will be 0 and this term will be extremely large. And if the answer is 1 and the neural network predicts 1, or if it's 0 and the neural network predicts 0, then you get 0. This is how binary cross entropy works. This is if you want to classify stuff into cat and non-cat, or cat and dog, or whatever. Okay, so now this is the most mathematical slide I have. And in order to explain how we train a neural network, we need to set up some notation. So I apologize in advance for this, but sort of to discuss this, we just need to go through these next two slides or so with this type of notation. So as I said in the beginning, or the way I introduced a neural network was I introduced it just as a composition of maps. And of course, if you have a composition of maps, you know how to take a derivative. It's just essentially chain rule. So at each layer, you want the gradient for each point in the data set. And now I want to introduce the following notation. So as we saw, essentially, the way you build this neural network is layer-wise. So I have this layer index up here, which is, in this case, I plus 1 here, or I here. And what you always do to go to the next layer is you multiply by a matrix and you add a vector. You add this bias. That's always W previous input plus B. And then you apply some nonlinear activation function to this. So you do the matrix multiplication, then you put it through some nonlinear activation function component-wise, and that gives you the next output. And this then you multiply again by a matrix, add a vector, put it through a nonlinearity, and this gives you the next layer, and so on. You put this back in here, and this is how you build layer by layer the neural network. So this is what all this notation is. A is the activation function. The superscript here is the layer you are at, and these mu's and nu's are the neurons, the labels of the different nodes in your computational graph, in your neural network graph. Okay, so before we go on, I want to just sort of show you what happens when you train a neural network. So what does this gradient descent do in practice? Okay, so I used one of the packages for for training neural networks. There are tons of packages out there. I use TensorFlow. In the tutorials, you will be using PyTorch. For the tutorials this afternoon, by the way, and at the end of the program, or at the end of the somewhere on the homepage, I tell you how to set up your computer so that you can run these different packages. So please do this before you come to the tutorials. Have this set up. If you don't want them set up locally, you can also do Google Colab. So you need an account for that. Just make sure you have it set up for the lecture, because in principle, you could just code all of this yourself. But in practice, I mean, experts at Google or Facebook or so have done this for you. And it's just very boring to do this yourself. And it's completely standard. It's matrix multiplication. It's taking gradients. So it's something that you could code, but of course you don't want to code. Anyway, so let me quickly illustrate how this training and learning procedure works. So in this case, I have taken a data set where I sort of take my input just from R1, some numbers between -2 and 2, and my output function, my desired output function, is assigned to the e to the x plus cosine of x. That's a random function I made up. If you plot it between -2 and 2, this is what this function looks like. And now the goal would be, in this case, a regression task where we try to learn this function with a neural network. So we can set up this neural network. It's very simple. So you see I add dense layers. So these would be the different hidden layers with 128 nodes and tangent activation function. And then in the end, I sort of take it down to one-dimensional output again by summing them all up. Now I just tell it to use the mean square error and optimize called Adam, and I iterate this for 100 epochs. So meaning now it does 100 times. It goes through this data set here that I produced here with these x and y pairs, and it does gradient descent on it. And then after 100 steps, this is the function that the neural network has learned. So you can see that it's not perfect. Of course, here it's deviating from the input, but overall it has captured the orange curve, which is the approximation of the neural network, the function that the neural network has learned, or the function that the neural network expresses by the parameters that you have updated using gradient descent is very similar to the one that you actually wanted to learn. So what you can do now is you can look at the last hit layer, at the last output, to see essentially how this function comes about. So in this setup, I have the last layer has 10 neurons, and they are all added up to produce this one-dimensional output here. And if you look at each of these 10 neurons individually, you find essentially this output. So you can see this is not, as I said, this is not learning a bunch of step functions. You can see essentially there are a bunch of tangents in here, because tangent is the activation function of this layer, but it's not doing this thing of adding a bunch of step functions. It's doing something different. I don't know what exactly it does. So this seems to be giving the overall trend to go up here, and then you have a bunch of things to pull it down here into the negative. And so, as I said, it's very difficult to interpret what the neural network does, but this is essentially the function that it has learned from updating the parameters. And if I was to run this again, this would look completely different. But when I sum all of these 10 up, I get an output that looks like this. And if I now was to train this, as I said, so initially you just get a random function, which would be in this case just this blue line. The orange one, sorry, the colors got inverted. So now the blue line is the neural network, and the orange line is the data. So initially this is just some random function here. And now I start training. So after 20 epochs or so, the function has become this. After 40 epochs, it looks like this. After 60, like this, 80 and 100 is the thing that we just saw. What I'm plotting here is the loss as it goes down during training. So this is the mean squared, the MSE, the mean squared error between what the neural network predicts at each point and what the output should be at each point. And you see this goes down. It probably would go further down. If I continue training this, you could probably get these points also right here. But this is how the function evolves, how by just changing these parameters, how the function that you see here changes as you train. And by doing this, as I said, in principle, you can get, if you make a neural network big enough, you can get any function you like. Are there questions on this?
It looked like the loss function was still going down at the end. Would you say that you didn't do enough training in this example?
Yeah, very good. So yeah, the loss continues to go down. So the question is, was this enough training? And it's an excellent question, and it's probably one of the hardest questions you can ask, because it's not clear what does it mean to have done enough training. So typically when you look at neural networks, they are not trained to the end. They are not trained until you have reached a minimum where, as I said before, where everything would be going up. So if you look at the Hessian or at the matrix, at the curvature matrix around the point you're sitting at, usually this doesn't have, I mean, you're not sitting in a minimum. Usually this has 0 eigenvalues, so positive and negative eigenvalues. So you typically don't want to train until you reach a minimum, or you don't even want to train until you reach a global minimum. If you reach this, every single point in here would be on top of every other point in there. This does not mean, and in general it will not, extrapolate then. So if I was then to plot this function from -3 to 3, of course I can just calculate this function from -3 to 3 as well. And typically it will match perfectly in the range from -2 to 2, but then it will start to deviate a lot. So this is the question of generalization. And as I said, typically if you train with gradient descent, if you take a big enough neural network and you train with gradient descent, your network generalizes very well. So it will give you something that's close to what you want to know, at least at points that are in between. And if you train to perfect convergence, typically, this is not a property that the neural networks still have. So it's extremely difficult to know when you have trained enough. And essentially one technique is what's called early stopping. So you actually stop before you have reached the minimum. And typically this leads to better results on unseen data. Of course, you know, on seen data, on data that you know the answer, it's wrong. And of course, on data that the neural network hasn't seen, it's also wrong, but it's very close. It's closer than if you have to train longer and longer and longer, you could get something that's called overfitting. And you would be in a regime where the result is not as good as you would have hoped. Yes.
You mentioned that if the initial conditions are different, you end up with different things in your last hidden layer, but the approximation presumably is still quite good. So in some sense, you're in each of those cases, you're finding a different local minimum, and yet somehow it doesn't really matter which one you find, they're all good. Is there like a simple way of understanding why that works?
Yes, so that's also an excellent question. So the question, repeat the question. The question was, if I was to just compile this notebook again and run it again, the initial function here would look different. It would be this, it would maybe look like this or so. It would be a different function, and even if it was the same function, if I was to change the parameters, the step size, and so on a little bit, the function that the parameters that I would obtain in the end would be very different. The function that is built out of these parameters would still look very similar, at least on this. So if I train long enough, sort of I can, with many different choices of parameters, I could get the same function, at least on this area from -2 to 2. So in a sense, the question is why does this work so well? Why does this combination of taking these huge neural networks and train them with gradient descent, why does this always produce such a good result, even though sort of my starting point is completely random, and essentially where I go is, well, it's determined by the gradient descent, but there are so many hyperparameters that there are also many different choices, tons of different local minima. This loss landscape is highly non-convex. I will end up somewhere, or I will stop on a slope because I'm not training to the end, and yet I get something that works like ChatGPT. As I said, ChatGPT was trained exactly once. You cannot afford to train it more. So essentially we have this random function that was trained and stopped somewhere. And why does this work so well? And there are many, many different hypotheses for how this works and why this works. There's no consensus in the community, as far as I know. There's something that's called the lottery ticket hypothesis. There's a hypothesis that neural networks learn simple functions. There's a attempt to explain this by saying if you go to an essentially infinite dimensional parameter space, every function is arbitrarily close to every randomly initialized function. So you need to just move a little bit in the parameter space to get to the function that you want. But it's an open issue, and a lot of research is actually going into how neural networks work and how they learn and what this training precisely does. But yeah, as I said, so lottery ticket hypothesis is perhaps one of the more recognized ones. So this says sort of you have this huge network, and inside this network you have some small subnet that already contains the correct function, and you have a bunch of other things that do some random stuff on top of it. So essentially by just turning off the random things or just having them cancel out against one another, you already have the function in there that you want. So this already won the lottery ticket essentially. And then the rest is just sort of stuff you can cancel out. So, but yeah, nobody knows. I mean, there's no common consensus in the community. Okay. Okay, so let's explain this gradient descent that we just saw in more detail. So yeah, the neural network, as I said, is a composition of maps, so we can use the chain rule. And at each step, sort of, we multiply by a matrix, add a bias, and then take a nonlinearity. So at the last layer, the output layer, you just want to know how the loss changes as you change the parameters of the last layer. So you are interested in dl by d theta n. And you can calculate this with the chain rule as dl by dzn, dzn by d theta n. And dzn by d theta n, you can just compute from here. So if theta, these thetas are all the parameters, if thetas are the parameters in your weights, essentially just get the derivative here just gives you this L nu. And if theta is the bias, this derivative here just gives you essentially a delta function here, delta mean. And you also know the derivative of the loss with respect to Zn. If it was the MSE loss, remember the MSE loss was y minus neural network squared. So if you take this derivative, you get, well, there was a sum 1 over n. So you get, now from the square, you get a 2 over n, and you get this, and then you get the derivative of the activation function. So that's the first step. This is how you compute the dependence of the parameters of the last layer. Now, if you want to compute the dependence of the parameters of the second to last layer, I can use chain rule twice, dl by dzn by dzn minus 1, dzn minus 1 by d theta n minus 1. This I already know. I computed this in the last step. This here is, again, just sort of, because it's wx plus b, it's just this derivative here times the derivative of the activation function. And for this dz by d theta, this is, again, just sort of either L or delta, depending on whether your parameter was W or was B. Now you have to resolve that the dependence of the loss on the parameters in the n minus first layer. Of course, you can just go down like this. dl by dzn, dzn by dzn minus 1, dzn minus 1 by dzn minus 2, dzn minus 2 by d theta. This is, again, sort of either W or delta. This one you have from up here, and this one you can just compute. So by doing this type of chain rule again and again, you get the dependence on loss, the thing that you want to minimize, over all the parameters in your network for each of the layers. And once you have this, you just do the gradient descent. You take the parameter and you update it by the gradient of the loss with respect to this parameter with some step size alpha. You take a step of size alpha into the direction which minimizes the loss. And you do this over and over and over again until you've either stopped or you've reached a minimum. Good. So that's the algorithm. What are the consequences of the algorithm? So most of what you actually need to calculate this here, you have already calculated to answer what the output actually is. We have calculated these sets, this W plus B, We have calculated the activation function. This all went into just sort of producing the output in the first place. So now we want to reuse this to train the neural network in the backward pass. But one thing that we haven't computed yet is the derivatives of the activation functions. You see they enter here, for example. We have A, but we don't have A prime. So one way of making your life easier is to choose an activation function where the derivative is itself a function of the function. So an example would be this logistic sigmoid function. If you have A of x is 1 over 1 plus e to the minus x, if you take the derivative of this, you can actually write this as A of x times 1 minus A of x. And A of x you have computed in the forward pass. So this takes 0 time to compute. You already have this information. Or if you take the tangent has the property, if you take the derivative of the tangent is just 1 minus tangent squared. Or you can take a function that's called a ReLU, so that's a 0 if it's smaller than 0, and it's 1 if it's, it's the identity if it's larger than 0, and of course, there I don't even need to store anything. I can just take the derivative of a linear function or of a piecewise linear function. I can just take it 0, 1. So that's why I showed you the tangent before, because it has this property. That's why this is kind of a popular, or sigmoid. That's why these are kind of popular, because just it's faster to train your neural network if you choose a function that has this property. Good. Another consequence is neural networks are typically used on big data, meaning millions or billions, or maybe like the internet, essentially infinite amount of data. And if you wanted to do this in any scalable way, of course, you need to be able to parallelize this over different machines or different cores. And if you look at a CPU, so if you buy a Threadripper from AMD, for example, this has 40 or 80 or whatever cores. If you buy a GPU, you have thousands of cores, and they are specialized for doing matrix multiplication, because sort of games, ray tracing, all these things require matrix multiplication. You have light ray that bounces off some surface, so your game wants to look cool, so you have to do some matrix multiplication to find out where the ray is going. So of course, now if you train something like ChatGPT with the internet, you can't fit the internet into the memory of your computer. So what you do is you batch your data, you break it down into smaller pieces. So instead of feeding it the internet, I feed it 100 words at a time. So, or instead of feeding it 10 megapixel images from a database of 1 million cats and dogs, I'm feeding it 100 images at a time. So this is what's called, I break it down into minute batches, like 10 or 100 images or words or whatever. And then I just train with these 100. I compute the loss landscape, not the entire loss landscape, it's just computed for these 100 images. I take a step, I take the next 100 images, I take a step, and so on. Or I'm just adding the different gradients on top of each other and then take a step. So what this does is this leads to what's called stochastic gradient descent. Instead of seeing the entire loss landscape, I'm just seeing the loss landscape for this 100 random images that I picked, and I'm just updating, pretending that nothing else was there. So I'm forgetting about big parts of my actual loss landscape, but just looking at 100 images and taking a step there. And then I look at the next 100, and I'm maybe going some other direction. If I had included these 200, maybe I would have had to go back, who knows. But I'm batching this, and I'm taking this more of a random or more of a stochastic approach of finding the minimum. But what this does is it helps to overcome, let's say, local minima or saddle points, because sort of a saddle point in the entire loss function might not be a saddle point if I just look at 100 images. So this helps me essentially to navigate the loss landscape better and to overcome points where my gradient descent would stop otherwise. So that's one of the things that sort of stochastic gradient descent does. The second thing is what was asked here before about the biases. So the reason why I mentioned this is because it gives a very nice intuition for what the weights and biases actually do. As we have seen, the gradient at the ith layer is proportional to the gradient at the I plus first layer. So what this means is as you backpropagate through your network, you always get sort of something that's proportional to the gradient of the layer before. And if your gradients are, let's say, 0.1, and you have a very deep neural network, you get 0.1 times 0.1 times 0.1, so you get a vanishing gradient, and the first parameters are not updated at all. Or if the gradients are 10, you get 10, 100, 1,000, a million, and so on. And then your gradients just explode. So if you make your neural network very deep, it's very, very hard to train these beasts. So what you can do is you can essentially clip the gradient. You say, okay, if the gradient is 10, I'm just walking 2, I'm never going further. I can normalize it. I can use the skip connections that I said, you skip one thing. So the gradient, even if the gradient vanishes, I still have the information from the layer before. But there's also something that's called edge of chaos initialization. This is actually extremely interesting because it gives you a feeling for what the weights and the biases do. So if you think about just at the first layer, you have Wx plus B, right? So what this is plotting here is the standard deviation of your draw from the weights and your standard deviation to draw from the biases. So if the weights are very, very big, so you have 2 points that are maybe very close to each other, but you multiply them by a huge matrix, what's happening is you're sort of putting things that are very close together, you're tearing them very far apart. You get some sort of chaotic behavior. Very tiny changes in the input lead to huge changes in the output. So if you make your weights too big, you're in this chaotic phase where you're just amplifying sort of tiny differences in input or even noise. If you make your biases very big, in contrast, let's say you just add 1 million to everything. So you get 1 million and you get 1,000,001 and you get 1,000,002 and you get 999,998. They're all of order 1 million now. So now you're in what's called the ordered phase, because no matter what your input was, you always get 1 million. So that's the other extreme. And then of course you look at this and you say, okay, there has to be something good in between. And this is what's called the edge of chaos here. This depends on the activation function. It depends on how big the variance of your input and so on. But if you normalize this, you get something like this. And if you write sitting, your weights and biases are carefully tuned to sit on this line. Your gradients will always be order 1. So they will not explode, they will not vanish. I mean, of course, if you're in the ordered phase, if everything is 1 million, independent of the input, the gradient is just 0. If you're in the chaotic phase, changing your input slightly will completely explode the gradients. And in between, there's the sweet spot where sort of changing them just changes the gradient just by the right amount. And in this paper, people have used this to train a neural network of depth 10,000. It's completely insane. If you try to do this without edge of chaos initialization, probably after 20 or 30, you give up. Either you get vanishing gradients or exploding gradients. So this is essentially what the weights and biases do in your neural network. And as I said, it's a consequence of training. It's a consequence of the fact that you always reuse the result from the I plus first layer in the ith layer. Another thing that's a consequence of gradient descent is what's called the dying ReLU problem. So if you look at ReLU, this was 0 for smaller than 0 and the identity for x larger than 0. So if something is smaller than 0, the function itself is 0 and the derivative is 0. So what this means is this activation function completely shuts off everything that comes after it. So if once this is smaller than 0, it's just 0 and all the updates are 0. So you're not sort of, you're just, the network after this part is just dying in a sense. So what people have done is sort of, instead of using exactly 0, they give this a small negative slope. And then the derivative is not exactly 0. And you get out of this problem that the network is completely shut off. And in some sense, for sigmoid, this can also happen. Sigmoid was this function that went between 0 and 1. It looked something like this. And of course, if you're very far out here, the function is 0 and the derivative is also almost 0. So to a less extent, you also have the problem with the sigmoid. But still, I mean, this is a theoretical problem. In practice, people still use ReLU, and it usually still works pretty well. But if you're worried, you can use something like give them small negative slope. Okay, this is actually all I wanted to say about training. And if there are no questions, I would then jump into transformers next. Okay. So with this basic idea of just as I said, matrix multiplication, activation, And training with backpropagation, you can essentially do all the things that are being done with neural networks nowadays. Now it just becomes a question of sort of finding clever ways of using matrix multiplication and so on to get very clever parameterizations of functions that can do something that the transformer can do or that ChatGPT can do. So this is the transformer architecture as presented in this paper here, and all the plots are actually taken from this paper. So the way this was introduced in this paper was the transformer was essentially performing a natural language task of a translation, for example. So the input would be an English sentence, the output would be a French or a German sentence or whatever. And you have this, this modular architecture where you have these, well, first of all, you have an encoding of the input, and then you have these attention heads, which find a good representation of your words, and then you put them into decoder, which essentially also has the same attention heads. And then in the end, it produces an output, which gives you the word, for example, the translation of the sentence, word by word. So let's go through what all of these things are. So the first thing you need to do is you need to feed a word to a computer. And of course, sort of, you need to translate it into zeros and ones, essentially, or into some float or whatever. So what is done in natural language processing is you need to map it into some Rn n-dimensional vector space. And usually the way you do this is you do what's called tokenization of the word or the alphabet. So let's say you take the Oxford English Dictionary, which has, I don't know how many, let's say 10,000 unique English words, and you enumerate each word from 1 to 10,000. And now I assign each word a point in a 10,000 dimensional vector space, which has a 1 at position I and 0 everywhere else. So the first word in the Oxford English Dictionary is A, so that would be 10000. Next word is aardvark, which is 01000. The last word is Ziziava. I don't know what that is actually. Maybe somebody in the audience knows, but this would be the 0001. Now I have this 10,000 dimensional vector. This is too big and too wasteful. So instead of working with this 10,000 dimensional vector, I want to put it into, let's say, a 512 dimensional vector space. So what I do is I multiply it by 512 times 10,000 dimensional matrix, which will map it into a 512 dimensional vector space. So multiplying the vector that corresponds to A by this will pick out the first column of this matrix, and multiplying this Ziva will produce this last column. Now I have a representation of each word in a 512 dimensional vector space. And by learning, for example, this matrix, you can learn a useful embedding. And people have shown that learning this matrix actually sort of does something very interesting. So for example, if you looked at the embedding of the word king in this 512 dimensional vector space, and queen and man and woman, you would see if you take the vector of queen, you subtract the vector from woman, you subtract the vector from woman, and you add the vector from man, you get to king. So queen minus woman plus man equals king. That's so the example. I'm not saying I'm not saying this has something to do with what happened in the UK or anything.
Fair enough. But what were you using? What information did you give it to train to learn? I mean,
good. So yeah. So the question was, when was this learned? So this is a very old example. Actually, I should have given the reference. I apologize. So this was what was called word to vec, and this was done in I think this was from a translation. And so you see it learns semantics, for example. You see it learns verb tenses, so walking minus walked is swimming minus swam. You see it learns country capitals, so Spain minus Madrid plus Rome is Italy, and stuff like this. It's by just doing this, it's learning a useful embedding. It's putting the words in this 512 dimensional vector space so that the position of these words have a meaning. Of course, putting A at 1000 and aardvark at 0100 doesn't have any meaning. It's just something that we came up with. But the neural network is then sort of extracting information like semantic relations of verb tenses and so on, and it's learning an embedding that makes it easier for it to process afterwards. Good. So that is the input embedding. Yes, sorry.
You gave it some, the people did, gave it some English track, so like some translations or something. But what is it that you're actually sort of minimizing or something to get this particular set of vectors? Like, did you?
Yeah, you're just asking it to translate from English to German, and sort of then you have a notion of. I mean, the question is always what is the loss function in this case? But there are sort of either you have it annotated, so you have you have a person sit down, or you have some sort of Rosetta Stone that translates it. I mean, you have the English and the German version of Wikipedia or something, and then there's a notion of, so if you introduce the notion of fuzziness on the words, there are, of course, like their score and so on, there are sort of different measures that tell you how good a translation is that linguists have come up with. And then you would just measure sort of how far away the output of the neural network of the translated sentence is from what a natural language, a person speaking this language would have produced as a translation.
Okay.
So what's happened is, so the matrix, you've trained it on this using the structure that you've got in order to get this matrix.
Yeah, exactly. So I asked it to find an embedding to then produce sort of, it got the word, let's say woman, it should produce femme. If it got the word moon, it should produce whatever moon is in French. Yeah.
So I think you're saying the input embedding is itself a neural network, but it was only a linear matrix. So is it like a different kind of?
So this, to some extent, this already happens, yeah, for just a single matrix. But of course, in the end, you will have again nonlinearities in a deeper one, and then the embedding, what's called the embedding layer, is the last layer before the output layer. So the thing that it used to produce the next word, let's say, or the translated word, just the last layer, the last hidden layer before you would produce the output from it. That's what generally is called the embedding layer in a deeper neural network. Okay, so now you have this 512-dimensional vector space, and if you train this matrix, you will have some sort of semantic already underlying, or if you don't train it, you will have at least a 512-dimensional vector instead of a 10,000-dimensional vector. So the next thing you need to do is you need to give it what's called a positional encoding. The reason is that, of course, the order of words matters in most languages. So the scientist eats the chicken is not the same as the chicken eats the scientist. So I need to know which word came first. And to do this, what people in this paper did is they just add a time modulated signal to each of these embedded words. So you have this 512-dimensional embedding of the word the, and then they just add sines and cosines to this 512-dimensional vector. Scientist is the next, so they just add sort of sine of, or in this case it was 1 over 10,000, because 10,000 was the size of the alphabet, and then some power of 0, 1, 2, 3, and so on of this thing. I mean, they just came up with something which is sort of a combination of sines and cosines that will tell you, if the sine, depending on how big the sine and the cosine is, this will tell you how far along in the sentence this word came. They say that sort of this is what they did, but they say sort of you could have chosen something else for the positional encoding. You just need to add some information that the neural network can use so that it knows which word came before or after which other word. Yes, please.
So in Latin, the word order doesn't matter at all. So if I'm translating English to Latin, would it be able to cope? Or?
It's a good question, and I'm not an expert. So I talked at a conference. I talked to a person, and I asked her this question as well. Or I also asked her, sort of, is English easier to learn than Chinese, for example? So, but they didn't have any information on that. I also don't know whether anybody, quote unquote, wasted money training a Latin translator. I really don't know. But yeah, I asked the same question and I didn't get an answer. So. I mean, worst case scenario, of course, the neural network ignores this information. I mean, you can put there whatever and it will learn what this means. Essentially, because if it's supposed to translate this, the scientist eats the chicken, into a language where the order does matter, let's say, then it would, if the signal tells it sort of in some way that scientists came before chicken, then this will be good. And of course, if you are translating from Latin where the order doesn't matter, then adding this will just sort of will not matter because it's already somehow in the grammar. Good. So now you have a 512 dimensional vector, which also has some time modulation on top so that you know where it was in the sentence. And now comes essentially the new part. So this has been, of course, known before. So now there's the attention mechanism. So the paper is called Attention is All You Need. This was sort of the new thing in the transformer. So we have now an encoded sequence of words with temporal information. And now we want to learn a useful representation of this data. So what the paper does is it uses this n times this gray box, where this gray box consists of an attention head, adding a norming, and then a usual feed-forward neural network, which is again added with these skip connections here. And they just do this 6 times. So they use 6 n of these blocks in the paper, n is 6, so they just do the 6 times, sort of attention, feed forward, pump it into the next attention head, feed forward, pump it into the next one, you repeat it 6 times, and then you have a function that reproduces some embedding into some vector space that is very useful for the translation task, or to predict the next word in ChatGPT or whatever. Good. So inside this encoder, you have, as I said, the first thing you have is this attention head. And this attention head itself has this modular structure. It has 3 inputs, as you can see here, which are called V, K, and Q, a value, key, and query. You multiply this by a linear matrix, each one of them. You pump it through what's called a scale dot product attention. You put the results together in one big vector, you multiply by a linear matrix, and then you put it into the feed-forward neural network. And this scale dot product attention, this is again just matrix multiplication, scaling, masking, applying a nonlinearity, matrix multiplication, and then you put it together, you multiply by matrices. So you see that essentially this architecture is very sophisticated, very complicated, but it boils down to matrix multiplication and nonlinear activation functions. And again, you train with backpropagation. You just take derivatives, and you get the updates of all the parameters that are in this linear matrix, in this linear matrix, in this linear matrix, and so on. So the idea that I introduced in the beginning is the same. It's just a very sophisticated way of putting this together. This network architecture is very complicated, but in the end, it's doing matrix multiplication. Good. So let's see in a little bit more detail what the self-attention does. So I have the embedding, the time variation, the embedding of the, and now I have these 3 matrices, the V matrix, the K matrix, and the O matrix. I take the word the, I multiply it by the V matrix, which in this case is 512 times 64 dimensional. This is what they choose in the paper. Of course, there's nothing special about these numbers. But all I'm doing now is I'm mapping this 512 dimensional vector, which had this temporal information on top of it, into a 64 dimensional vector space. And then I'm doing this again with a second matrix. So I'm mapping it into a second 64 dimensional vector space, which is called the K vector space. And I'm doing it the third time, and I'm mapping it again into a 64 dimensional vector space, which is the query vector space. So all I've done is I've taken this one word, I've multiplied it with 3 different matrices, and now I have sort of 3 different embeddings into 3 64 dimensional vector spaces. And I do the same with the scientist and with eats and the chicken. So now I have an embedding of these words in the sentence into these 3 different 64 dimensional vector spaces for each word. And of course, again, sort of these, as I said, these matrices here, they are learnable parameters, these V's, and so they will be updated during gradient descent. Good. So now I have the set of 64 dimensional vectors, the query, the key, and the value. And what I do now is I compute a score of how much sort of they are related, how much they are overlapping, how important one word is to understand the other word in the sentence. This is what I need to pay attention to. This is where the word is coming from. So this is really the gist of it. So I compute a score between the current word and the other words in the input sentence. And the idea is the higher the score is, the more relevant this word is to understanding the other word in the sentence. So the way I compute this is I take the dot product. So if you know sort of from linear algebra or from quantum mechanics or whatever, the dot product measures the overlap between two vectors. So if the vectors are essentially orthogonal, the dot product is 0. And if they're very much aligned, there's a big overlap between them, the dot product is pretty big. Then they scale it to avoid gradient blow-ups and so on. So this is not, so there's nothing deep there. They just multiply it by 1 over square root of 64. Then you can mask some of the inputs if you don't want your neural network to cheat by looking ahead. You can just say, okay, you have to work with what you've seen already. You cannot look sort of what the rest is. You can do this so you can do this mask. Then you apply a softmax. The softmax, all this does is it's a activation function which essentially takes all the 64 outputs and makes sure that they sum to 1. Now you have an interpretation of a probability, because yeah, sort of some entries are bigger, some entries are smaller, but they will sum to 100%. Yes.
Your last slide.
Yes.
At what point is this sine and cosine that embeds the position?
Good. So the sine and cosine is already in this vector the here. So this is after you did. You first take this embedding. You take 10,000. You take the 100. You multiply it by 10,000 times 512 matrix. You map it into a 512 dimensional vector space. You add sines and cosines. And now you have this vector the, which is a 512 dimensional vector, which has the sines and cosines in them. And now I do this multi-head attention magic, where I multiply this vector the, which is this 512 dimensional vector, plus the sines and cosines I multiply by these matrices V and K and Q for each word. Yeah, thank you for the question. Sorry?
Basically?
A cubic? No, it does something else. Let me show what it does. So it computes essentially the overlap between the query and the K. This gives it the score, and this score is multiplied then by the value. Yeah, so you take the Q and the K, you take the dot product, you scale it, and then you multiply this overlap with the value that is also computed from these words. So this is a little bit, so these words come essentially from databases like queries and keys, and so this is lingo that is buried from databases. So what you do is you have essentially two words and you want to know how close they are together. So you calculate essentially overlaps between these. This is what these Q and these K matrices are. And then you also calculate values for each thing. So then you take how much they overlap times the value. So it might be there's a big overlap between them, but it's not valuable to know this at this point. So then the overlap would be big, but the value of knowing that they overlap would still be small. So this is essentially, in a nutshell, what you do. You take the dot product between the queries and the keys. You scale it down by the square root of 64 to make it a non-exploding gradient. Turn it into probability, and then you multiply by the values. So in a nutshell, this is what it's not a cubic. It's this. I mean, it's almost like a trilinear, but there's a softmax in between. So. Yeah. So you calculate overlaps between vectors and then multiply by values, and all these are just gotten by, again, sort of learning a useful embedding of these of the scientist eats the chicken. By multiplying this just by matrices, you learn what good values are, what good query values are, and what good key values are. Yes.
Just a quick question about the adding up the different words. The way you said it, described it, it said that you said the embedding kind of captures relations in vector differences. So why should we expect the vector sum to mean anything in this context?
Yeah, so this is good. So the question was why Why is it the sum of the vectors and not something else? Well, so the way, sort of almost by definition, it's the last layer before the output of the neural network. So after that, you just sum them up to get a result. So this is why it's encoded in the sum. I mean, the last step is usually the last activation function is just an identity. So you just multiply, in the end, you just multiply by a matrix and just add up the different vectors, maybe weighted by some finite matrix. Yeah. Yes. I mean, it's beneficial to know sort of to go from queen to king is essentially the same as going from man to woman plus some extra information. I mean, traditionally a queen was female and a king was male. So going sort of between them, of course, a queen is or was a very specific type of female person, with a female person which was inheriting the title essentially. And the king is also was a male person was inheriting a title. So it's useful to know this because many things will still carry over just from the relation between man and woman, or maybe so for example, if you were translating to German, knowing whether something is male or female will change the next word. We'll add an E at the end of the next word in French as well. So and this will happen irrespectively of whether it's any man or any woman or if it's a king or a queen.
In the example you just gave of adding an E to the end because of the male or female word earlier in the sentence, is it simple to see how that fits into these three matrices? I still don't see how that, how does that turn into this function?
Good. So the question is, how can I see this, that this happens in this function? It's a good question. I've never thought about it. So the embedding would then be in a way such that the overlap between king and queen and man and woman would probably be the same.
One word to the third word down the sentence or something.
So let me show you what V does in more detail here. So what this is this is again taken from the paper as everything as all the plots here. So what this is showing is a different sentence. The law will never be perfect, but its application should be just. This is what we are missing, in my opinion. So this is the sentence at your input. And now what they did is they trained this on translating this into German or French. And they looked at each of these 6 different attention layers. They looked at what the scalar product of Q times K softmax times V actually was. So what was it paying attention to when it saw the word it's, for example? And when it sees it's paying attention to law. So this is what it's involved in and a power resolution. So to know what it refers to, of course, and it could refer to anything here. And the overlap of it's with other things could be large, but then after or small, but then multiplying with the value. So the combination of Q times K softmax V singles out paying attention to the word law here. So you know that it's represents the word law with this combination of multiplying by the value. I mean, taking the overlap and then multiplying with the value. So this was what's going on in the 5th attention head, and in the 6th attention head, there was also attention to application. And if you just looked at essentially just at all attentions that are paid in the 5th layer by the 5th attention head, you see again, so it's and law. Law also pays attention to itself, and law pays attention to its article. Most words actually just pay attention to themselves, but then there are also these other relations. So the darker the color, the more attention is paid between these different words. So the bigger either the overlap or the value. I mean, this combined thing of taking Q times K times V is. And so we cannot interpret it, but we can look at this. So you can actually look what this thing is paying attention to. And people have used this in other setups, for example, playing StarCraft or so. So you can look at the minimap and you can, so StarCraft is a real-time strategy game where you need to build a base and build an army and defeat an opponent. And you can see sort of at which point you can look at these attention layers and you can see what the game is. I mean, how the thing is playing the game, what it is paying attention to at every single moment. And in the case of translation, you can see sort of that it's paying attention to law. How it figured this out, one second, sorry. How it figured this out, we don't know because we don't understand this billion dimensional parameter space, but we can at least see that this is what it does in the end, just as we could see that sort of king minus queen is man minus woman. Yes, please.
So it's like it's paying attention to the different words, looking at queen and king. It's same as the words, like different words paying attention to male and female. So it's identifying like those different words are the same group of words.
So they would be embedded in different positions, but sort of the difference of the embedding in the positions would be the same, or the overlap between man and woman would be the same overlap essentially between king and queen.
So that's why the equation could be identified by it.
Yeah, so that's why in the end, by adding up, yes, you produce you get this linear relation between them.
What would happen if I reduce the dimensionality of the embedding layer, like instead of 512, let's say like 32? Do I reduce the number of concepts I can?
Good. So the question was, what happens if you reduce the dimension of the embedding layer? And again, I mean, this is one of the many hyperparameters you have in there, and there's no informed way of knowing what is good or bad. I mean, of course, you see if I make it one-dimensional or zero-dimensional, you lose all the information. I could have kept it 10,000 dimensional, but that's wasteful, and I couldn't probably train it with any reasonable amount of money. So this is a trade-off of making it a sort of smallish enough so that you can deal with it. I don't think so, because people don't understand how any of this really works. Even though the function is completely explicit, this is essentially sort of hyperparameter optimization is essentially some trial and error thing. Yeah, so you can, in contrast to this nice picture with the weights and the biases where you could sort of essentially see what they were doing, it's very hard to say sort of 512 is the sweet spot here. So there's no edge of chaos analog for the dimensionality of the embedding space, as far as I know.
Hey, on the previous slide, when you've got these Q, K, and V, so, yes, Q, K, and V, it looks like everything's symmetric in Q and K. And so at the beginning, you initialize to random parameters. What breaks the degeneracy between Q and K?
I mean, yeah, they are very similar. They are just different matrices that are learned differently from, I mean, you just take the same word the, and then you learn a matrix that multiplies the word the to embed it in some 64-dimensional vector space, and you do the same with K. I mean, yeah, one is essentially the transpose of another here.
Similar to the question just said, as in, I guess what I'm curious about is like, why do you have to have two separate matrices? Why can't Q and K just be basically made into one, or just one vector, one thing that you train on? Why do you have to train two separate matrices and then multiply them together?
So the question is, why do you even need to? Well, I mean, so you can exchange them, but they are still different matrices. There still is I mean, otherwise you would have the same matrix to calculate the overlap. So if you had then the query of so otherwise the scalar product between two vectors in the same row would always have like maximum overlap. So the overlap can still be different between the Q and the K, but you still have the symmetry of exchanging them. Okay, so we are running a little bit late. It's great, it's interactive, and I'm almost done. So let me just sort of briefly recap what we have seen. So you take a sentence, the scientist eats the chicken, end of sentence token. You learn an input embedding by multiplying these 10,000 dimensional vectors by a 10,000 by 512 matrix. You produce this vector from it. You add the sines and cosines on top of it. So you obtain a new 512 dimensional vector. You put it into multi-head attention, meaning you multiply it by the weights, by the queries, the keys, and the vector matrices. You calculate this score essentially from it. And then you put this together in one big vector again. You calculate, put it to standard feed-forward neural network. You repeat it 6 times. Put it to the feed-forward. In this case, they use the ReLU here. You add it all together. You repeat it 6 times. And you get this embedding of the sentence. Now you have an input encoder. Now you have exactly the same thing on the decoder side here. It's again multi-head attention, which uses essentially the output that you have already produced plus the input embedding of the next word. So if you want to translate the sentence, let's say the scientist eats the chicken, and let's say I've already translated it into German, so I've already translated the scientist, der Forscher, and then the next word would be eats. So you would have eats come in here, and the output that it already has produced, der Forscher, and then you would have the Forscher and eats go in here, and then you would produce what the next word should be, ist in this case then. So this works exactly in the same way. You just go through this, and then in the very end, you have this information, you pump it through one last linear layer that maps it back into a 10,000 dimensional input space. Because we were in this 512 dimensional input space, we map it back into 10,000 dimensions. We take the softmax. So now one of the entries will be the biggest. Let's say it's entry 782. So I open my Oxford English Dictionary, I check what the 712th word is, and I use this word to be the next word to follow. And in ChatGPT, essentially I take whatever the input of the user was, plus whatever I have already answered to the user, to compute what the next word that I should answer, that should be in my answer is. And then once I've added this word, I go to the next, essentially I go to the next, I include this word, and I find the next word, and so on. So this is how you build up sequentially from the information that you already have, what the next word in the answer should be. Okay, that's just my recap. So you said neural networks for regression classification, just they learn some complicated function, and they can learn any function you like. We trained with gradient descent, and we saw that sort of this has implications for exploding or vanishing gradients. So you have to sort of add some tricks here. We talked about natural language processing, explained the transformer architecture and this semantic embedding. And before I close, I wanted to invite you, or say if you want to learn more, there are meetings for mathematics and machine learning at Caltech, and for string theory machine learning afterwards in December. And we are hosting an Aspen Winter Conference on field strings and deep learning in January next year. And the application deadline is coming up. So if you're interested in any of this, check out the website to let me know. And with that, I just want to thank you and see whether there are more questions.
We are taking a break now, a coffee break. I think we can be back at 11:05. So a 25-minute break.
managed to make up for the 10 minutes I lost at the beginning. So